Okay, so good afternoon again, everyone. Welcome to APNIC eLearning web class. Today is the 6th of April in 2016. It's 1 o'clock in the afternoon. I'm not sure whether it's still early morning from your end, but anyways, welcome to our session. This is the second session, and we will be discussing about IPv6 addressing and subnetting. Now, before we proceed, I would like, as usual, just want to introduce myself. I can see that some of you here are the same people that were in my class earlier, so but I think at least one is new. But just very briefly, I'm Sheryl Hermoso. I'm from training team at APNIC, and we are a team that conducts face-to-face workshops and online sessions to members of the internet community in the Asia-Pacific region. We cover different topics, particularly IPv6, routing, BGP, MPLS, network security, DNS and DNSSEC, and internet resource management. Okay, one person in the class can't hear me. I'm not sure why. It seems okay for the rest. We will try to make some adjustments from our side, just maybe ramp up the audio a little bit. But can you also please check from your end? I know you were in the class earlier, so maybe just check. Okay, let's just figure out first if there is anything wrong with the connection. Can you hear me now? Is the audio better? Not getting any response from him, so I'm not exactly sure. Everyone else is still okay with the audio, hopefully. So just give us a couple of minutes to see what was the issue with this. Okay, I can see he rejoined as another account. Can you hear me now? Is the audio better? If you can hear me, not yet. Actually not very sure because it seems okay with the rest of the class. Everyone else is not having any issues, right? Okay, it's okay with Dinesh. So it seems that it's a problem from your end, apparently. Sorry about that. We will wait a few minutes. Sorry for the rest of the class. Let's wait a few minutes for, so I think it's Manjula. See whether he can resolve the issue before we proceed. Because he's taken the time to join the session, so let's let's cater for that. How about now? Is the audio better? Okay, I'll just say a few things about IPv6 while he's trying to resolve the issue, right? I'm just gonna talk about an overview, a little bit of IPv6. For those of you who have not attended the first session today. So as we said, okay, he said okay. So I think that means you can hear me now, right? As I've said, this session is about IPv6 addressing and subnetting. So it comes after the session on the introduction or overview of IPv6. So what is IPv6? It's a new protocol that is meant to not exactly replace, but complement IPv4. The main issue that we have with IPv4 right now is we are running out of IPv4 addresses. We don't have enough. We have reached a point where we are now using from the final 5/8 IP addresses, which means there's no more IPv4 within IANA. So IANA is Internet Assigned Numbers Authority that maintains the entire IP address pool. So the solutions we were looking at is IPv6. In this session, we will look at the differences. Well, not exactly just the differences, but one main thing is how do you write down, how do you represent IPv6 address, and what are the different types of addresses? From one point to the other, I will be referring to IPv4 just to give you kind of like a background, a way to compare what the differences are, and we will build our knowledge of IPv6 addresses from there. Now, just as a reminder, by the way, that at the end of this session, again, we will be having a short survey for you. So if you can just click the link that I'll be posting at the end, that will be very helpful for us. So let me just check with Manjula if you can hear me now. Okay, so what are we going to cover? So these are the things. I'll first be looking at IPv6 address text representation. We'll look at IPv6 addressing structure and address management hierarchy. How do you distribute IPv6 addresses from the RIRs to the LIRs and then to your customers and members? We will look at different types of IPv6 addresses. In IPv4, we have something like public address and private address. Now, what are the different types of IPv6 addresses in IPv6? We have a few for local addresses. It's not just one. And then for global address, we have that as well. That's globally reachable IPv6 address. Now, there are different parts of IPv6 address, and half of that, the last 64 bits, is called interface ID. What is interface ID? So we will look at that as we go on. And then at the end, we will have some examples of auto configuration, how that happens. We said that one characteristic of IPv6 is that you don't need or you don't have broadcast. There's no support for broadcast at all. So how can you now reach another machine, okay, via IPv6? So that's done using auto configuration, and let's look at the process of looking or finding other devices using that. We will have some subnetting examples, okay? So when you have your V6 ready, you can now subnet it into smaller blocks that can be given away to your customers. Okay, so I haven't heard from Angela at all, so I think he probably hears me now, hopefully. So let's proceed with the class. The first one is IPv6 addressing. Now, let's make things easy for everyone, okay? IPv6 address is 128 bits long, okay? That's a very basic thing that you have to understand. It's not 32 bits. IPv4 is 32 bits long, okay? IPv6, when it comes to the size of the address only, it's 4 times bigger, which is 128. Now, when you look at the entire IPv6 address pool, it's not just 4 times bigger than IPv6, than IPv4. We're talking about exponents here, exponentials. So from 2 raised to 32, which is 4.3 billion in IPv4, in V6, that's actually 2 raised to 128, which is 3.4 billion addresses in that IPv6 address space. So it's not 4 times bigger, right? But the address itself, the number of bits, it's 4 times bigger than IPv4. It's 128 bits. In IPv6, we call every 4 bits as a nibble. So you hear me talking a lot about nibbles. If you look at conversations in mailing lists in IETF, they refer to 4 bits as nibble. Okay, it's a representation of a hex digit. Okay, so you can either call it a hex or a nibble. So the way that you write down an IPv6 address is actually not using dotted decimal format. Okay, let me just step back a little bit. IPv4, we're all familiar with that. How do you write down an IPv4 address? Clearly, you don't write the entire 32 bits, right? You use a text representation. It's called dotted decimal format. You have 32 bits, you divide that into 4. So each octet or each 8 bits, you represent that as a decimal. And then you Okay, separate all of those octets by a dot. That's why it's called dotted decimal. Okay, each octet is represented by a dot. So you have from 0.0.0.0 all the way to 255.255.255.255. That's your entire range for IPv4. Now for IPv6, you don't represent it as dotted decimal anymore. It's too long. So instead of using decimals, we are using hex. We're using hexadecimal digits. So the entire IPv6 address, okay, so you divide your 128 by 4, because each hex digit, okay, will be 4 bits. So representation-wise, it's actually 32 hexadecimal digits or 32 nibbles. Okay, now this example that you can find here is just one of many IPv6 addresses. 2001:DC0:A910::. Now we will explain in the next slide why and how this is represented. Okay, this one is just for you to become a little bit familiar with an IPv6 address. So if you see something written in hex format, okay, hex meaning from 0 all the way to F values, okay, and then separated by a colon, that is an IPv6 address. Notice that each of the fields, so fields are separated by colons, each of the field will have 4 hex digits or 32 bits. So A is 1010, 9 is 1001, 1 here is 0001, and of course 0 is 4 zeros here. Okay, so I hope that gives you a bit of an idea of IPv6 representation. So this one is just a summary of that. It's hexadecimal values, so you have 16 bits per field. Each field is separated by a colon. Okay, so each X value here is 16 bits, and then you have 8 possible fields in here. So 8 X's here separated by a colon. Okay, or 4 hex digits for each of the fields. Now, a complete example of an IPv6 address is this one: FE80, DCE3, 124C, etc., etc. If you count that, there should be 8 fields, again separated by colons. If you can see those ones there, right? And then each of them should have 4 hex digits or 16 bits. Now, normally, like in the previous slide, you don't usually, at least for now, you don't usually see an entire IPv6 address like this. Why? Because some of them have been abbreviated. Okay? When you have an IPv6 address that has a lot of zeros, you can actually remove some of those zeros so that it's easier to write down. It's for humans, it's for us, it's not for the machine, because at the end of the day, the machine will still convert it back to bits and then represent it as such. But for us humans, it's easier if you have smaller number of digits, so you'll try to remove some of those zeros. The way that you can remove them is based on this rule. One is if you have leading zero. A leading zero is a 0 on the leftmost side of your field. So each field has 4 hexes, right? 4 hex digits. This is a field, okay, 0 db8. So what can you do there? Remove the 0 because it's on the leftmost side. So just represent it as db8. Same with these ones. These are all zeros, right? So just remove all the 3 leading zeros. So you'll have 0 there. Another one, 036E. How do you represent this? Very simple. You just remove the first 0, so you have 36E. Now remember, that doesn't apply for values or zeros that are on the rightmost side. So 1250 is still 1250, obviously, and 2B00 is still 2B00. Only leading zeros, only zeros that are on the leftmost side you can remove. Another one, if you have groups of zeros that are adjacent to each other. So you have the first one, you can see that very clearly because you have 3 fields here that are all zeros. Or if you look at the second line, all these 3 zeros, okay, you've already kind of abbreviated a little bit, but you still have 3 fields that are all zeros. What can you do? you can remove all of them. That's the beauty with IPv6. You can remove all of that and then just represent it with a double colon. Okay, so you use a double colon, or sometimes we also call it as a null value. Okay, so all of that will be replaced. Now, one main rule about this, a double colon can only be used once in an IPv6 address. Why? Let's look at an example. Let's say, for example, here, I'll just write it on the chat. It's easier for me rather than typing something away on the presentation. So let's say, for example, we're using the same one. It's 2001 db8 colon 0 colon 0 colon 0 colon 36e colon 0 colon 0. So we're just changing the last two fields here with all zeros. Now, what is the right way to represent this? Okay, you can remove, of course, the first set. So you have 2001 colon db8 colon 36e colon 0 colon 0. That's one possible answer. Or you can also change the last part, this part on the rightmost side, in which case you'll have 2001 colon db8 colon 0 colon 0 colon 0 colon 36e double colon. Does that make sense? So two possible answers. 240, sorry, I think it's not 2400, it's 2001, sorry about that, db8 colon 36e 0 colon 0. This is one possible answer. The other one that I mentioned is 2001 db8 colon 0 colon 0 colon 0 colon 36e double colon. They are both possible, but you cannot use you cannot use the rule to replace both of those adjacent zeros. Only once in an IPv6 address. Why? Because it will result in confusion. It will be vague. You don't know how many zeros are represented by one double colon, right? So with this, with the first answer, you know that it represents 3. Because the entire number of fields in an IPv6 address should be 8. And you have 5 there, meaning the double colon represents 3. In the second example, it's the same. Okay, you have 6 fields, and then the last 2 are represented by a double colon. Okay, does that make sense? Again, main rule in IPv6, if you have a group of adjacent 0 fields, you can remove that and represent with a double colon, but only use that once in an IPv6 address. Okay? Now, some rules about this. According to RFC 5952, the recommendation is to replace the rightmost set of 0 fields for consistency. So, meaning in our example earlier, you use the second answer. So, 0 colon 0 colon 0 colon 36e colon colon. But obviously, this is just a representation. It will still be up to you. If you want to replace the ones that has the most number of fields, that's also okay. Now, usually, this double colon, you choose the one on the rightmost because it usually represents the prefix, meaning the block that you are assigning to a subnet. Let's look at this last one. 2001 db8 colon 12 colon slash 40. So this is the block that you are using. This is the prefix that you're using for that network. So everything else that follows will either be a smaller subnet or the, well, we will explain this earlier, the interface ID, meaning the representation of the entire address for a single machine. Okay, the entire IP address. So you have there your network field, followed by a double colon, and then the rest here, whatever you will put there later on, will be the address assigned specifically for that machine. That's another way to look at it. You use the double colon on that side to kind of like separate or differentiate the network bits and the host bits. Another one thing that you should know if you are writing an IPv6 address in a URL. Say you're doing some troubleshooting or diagnostics. Say your web server is not accessible using its FQDN or its web address. So you try to use an IP address, right? Like you would in an IPv4 address. Now here in IPv6, it should be enclosed with a bracket. Why? Because of the colon. In typical, say, browser, they would represent anything that follows a colon as a port number, because that's how you do it in IPv4. You have 192.168.1.1 colon 8080 for your web server. That colon 8080 is your port, right? In IPv6, okay, to differentiate that, because whatever follows a colon is your port number, you enclose IPv6 address in a bracket. But obviously, you don't want to do that all the time. Only when you're doing troubleshooting. Otherwise, use the domain name, the fully qualified domain name for that server. Okay, now one very important thing in IPv6, make sure that all your prefixes will have a prefix length. It always usually comes together. So the 2001 db8:12, there is a /40. Because if you only use the :12:::, you're not sure. How big is this? Okay, how big is this prefix? /40, /48, /32, you don't know. So it always comes together. You represent your IPv6 address with the address itself plus the prefix length. So this is an example of an entire IPv6 address, so we can have a visual view of, say, in bits, how big it really is. So it's always good to represent it in hex because of that. Okay, next part is IPv6 addressing structure. Now we have an idea of how to represent an IPv6 address. The next stage for us, I suppose, is to understand the kind of the parts. And from there, okay, what follows is an understanding on how it's distributed. So let's look at this top one. We said that IPv6 has how many bits? 128. So here you have from 0 to 127 or 1 to 128, depends on how you want to represent it. So from the first 64 bits, the higher order 64 bits, and then you have the lower order 64 bits on this side. The higher order bits is what we call as a network prefix. Remember, in this previous example, just very quickly, this is representing this part here is kind of your network prefix, right? Now, this last 64 bits is your interface ID. So, think about IPv4 for a little bit. In IPv4, you have the host bits and the network bits. It's kind of similar to that. Obviously, there are some differences, but simplistically, if you looked at this, that's kind of how it's like in IPv4. The network prefix represent your entire network bits or your subnet for that network. And then this interface ID is what you add to complete this address and assign to a machine, to a device. Okay, here let's look more closely on the network prefix first. So normally, okay, from this 128 bits, you only do your subnetting, okay? So you only divide your IPv6 address and within the first 64. So you'll have this first 32 is usually what you get from your upstream provider, from your RIR. So let's look at it this way. If you are going to request for your IPv6, how much block size would you normally get? Typically, it's /32. Why? Because that's coming directly from the RIR. Okay, if you are requesting for a portable address for further subdivision or distribution to your customers as an ISP or some local internet registry, you'll normally get a /32. So when you say 32, that's this block from 0 to 31 bits. Okay, from that, you're the ISP now. You have that /32 block. You're now going to distribute that to whom? To your customers. Maybe it's home users, maybe it's SOHO or small office, home office type of network, maybe it's a large enterprise network, maybe it's a very big multinational company that is your customer. So it can depend, right? So as an ISP, you would normally distribute somewhere in between 64 and 48. Now let's assume for a little bit that all your customers okay, are big customers, and you want to delegate /48 for each of them. That means that for your /32, you can have a, possibly 2 raised to 16 customers. Okay, that's the difference between 32 and 48. You can have 2 raised to 16 customers for your ISP, for that /32. Okay, now if you have very small customers or home users, individual users, maybe you just need to give them /64. Now, why are we limiting ourselves to this 64? From this 64 forward to here, to 128, it's already your interface ID. It's kind of like right now, this is your limit. Most operating systems right now don't really understand anything that's smaller than a /64. So if you provide it with an IP address, okay, normally it will assume the size 64. Okay, that's one of the main reasons why we have this. And partly because like in the when IPv6 was designed, which is like a while ago, okay, they think that this should be enough for that kind of like distribution. Okay, so you only limit yourself to /64. So if you have very small customer, which needs only a single subnet, you get a /64. If you have bigger customer, you might want to give them something that's bigger. You can play along the nibble, maybe /60, /56, /48. Okay, work yourself along the nibble. Now, it will be up to you as a service provider to give whatever block size you want to give your customer. It depends on your agreement. It depends on your own policies. Okay, but as a general rule, it should be playing along the nibbles between 64 and 48. Any questions in this? I hope this is very clear to you. Okay. You can obviously say for a single machine, okay, this is generally what's the case, right? So if you have 2 or 3 or maybe just 100 machines, they're all connected to the same network, same subnet, you give them a /64. If you have 5 computers in that network, you still give them a /64. Okay, that's the smallest subnet that you will give to one node or one subnet. Does that make sense? So when we look at different types of IPv6 addresses later on, notice that our focus is only on this part, only on the network prefix. I hope that's clear. Okay, later on, we will talk about interface ID, but in the next few slides, our focus is on the network prefix for now. I can see Dinesh typing, but if anyone also has a question, please feel free to write them down. I'm just going to continue, but then when I read your question there, I'll try to answer as soon as possible. Okay, now let's discuss about IPv6 addressing models. So there are 3 in IPv6. There are 4 in IPv4. Okay, so one of them is missing. So just as a review, let's discuss each of them just very quickly. Unicast is one-to-one, right? You have a single machine, single interface. The destination is also a single interface. That's unicast. We have unicast in IPv4. Now, these two, next to here, anycast and multicast, are kind of similar to each other. So it's one-to-many. So one source, one source address, and then multiple destination. Okay, the destination address, okay, is essentially just one address, but it's either multicast or anycast, meaning it can be assigned to different machines. Now, the main difference with multicast and anycast is that, say, when you have multicast, I have a packet, I'm sending out that packet, it will be received by all the others that have the same destination address. Okay, what is the meaning of this end of IP? Okay, can you please clarify that, because I'm not sure what you're referring, if you're referring to the previous slide or this slide. Maybe it's the previous slide. Do you mean this? Oh, you have that? I'll describe that later on, but it's essentially a zone ID. It's not part of your IPv6 address, but because you have different possible networks that you're belonging to, because you can assign multiple IP addresses on the same interface, we have something called zone ID. Okay, so different operating systems represent zone IDs differently. Yours is percentage something. Okay, it's generated by your machine. Okay, it's unique on your machine, and it's the representation done in Microsoft Windows, I think, and then in Mac and Linux, it's usually EN1, EN0, something like that. Okay, so I have a slide, I think, dedicated to it. I'll describe it in more detail. Okay, going back to this. So unicast, anycast, multicast. As I've said, when you say multicast, it's sent from one machine to multiple machines. Kind of like if I'm a member of a mailing list. If I created my email, if I compose an email, send it across to the address of the mailing list, it will be received by everyone that's part of that mailing list, right? So multicast is like that. You have many machines, they have the same multicast address. When I send a packet to that destination, everyone will receive it. Anycast, on the other hand, is also sent the same way. It's sent to the Anycast address. You have multiple machines that are configured to use the Anycast address, but only a single machine will receive the actual packet. Okay, only the closest. And when you say closest in this case, it's not something that like closest when it comes to say geographical distance. It's based on routing. It's based on some attributes and things like that. So one machine will receive it. Now in IPv6 we use this 3. Obviously the main thing is we don't use broadcast. Now as we move on, we will discuss different types of IPv6 addresses. And some of them will fall under unicast, some of them will be anycast, some of them will be multicast. So you know what the functions of each one, right? So at the back of your head, when we discuss each type, please remember whether they fall under unicast, anycast, or multicast. Okay, can you please do that? All right, let's discuss the different addresses now. I remember one of you in the previous class asked about how many, can I use IP address only in a single interface or more? Actually, you can use multiple IPv6 addresses in a single interface. And we will look at what types of v6 addresses can be added to it. First of all, we have these addresses without prefixes, things like loopback address and unspecified address. In IPv4, loopback address is 127.0.0.1. In IPv6, it's ::1/128. Why is it ::1? Obviously, because all the others, the leftmost part, are all zeros. And what did we say? If you have multiple adjacent zeros, you can simplify it, okay, and represent it with a double colon. That's exactly what we did here. So that's why you have ::1 and then include the prefix, okay, the prefix length here, which is /128. /128 refers to a single IP address. In IPv4, that's kind of equivalent to /32. Okay, you're referring only to a single IP address. That's your loopback. Now, unspecified address, very similar. It's : /128. : because they're all zeros. So you can easily write it as : /128. We also have two things here that is used for transition: IPv4 MAC address and IPv4 compatible address. So what are these? It's normally for transition between v4 and v6. So you have an address you can assign for IPv6, but in the last 32 bits will be IPv4. So if you are in an environment where you are running IPv4 only, the last 32 bits will be used as your IPv4 address. But if you're running in an IPv6 environment, then you use the entire variable, and that's your IPv6 address. That's why here, if you notice, we're using prefix length as /96. Okay, only the first /96, because the last 32 bits there is your IPv4 address. So normally this is something like we see it as : :FFFF:1into.168.0.1. That's just a representation. Again, it will be converted back to bits later on. But for us to easily see it, you know which one is the IPv4 part and the IPv6 part. Okay? All right. Now this one's, okay, we've already discussed the first two. Now we will focus on the last 4. The first one is global unicast address, and this is the range 2000/3. Link local address is FE80. Multicast address is FF00/8. and unique local address is FC00/7. Don't worry, we will discuss each of them in the next few slides. But here is for you to be familiar. So if you see an IPv6 address, oh, it starts with FF00. What type of IPv6 address is it? It's a multicast address. If you see something that starts with FE80, oh, it's a link local address. If you see something that starts with FC00, you know that it's only a local address. Now let's look at the function of each. Let's start with the first one, which is link local address. Link local address uses this network prefix FE80::10. Okay, anything that starts with FE80 is a link local address. Notice that link local address is a mandatory address. It's a special address. So the moment that you enable IPv6 on your machine, on your interface, it will have a mandatory IPv6 address, and that is your link local address. So if you do that now, have a look at your own machines. Most Windows machines, even Linux and Mac machines, have IPv6 enabled by default. So if you do a simple ifconfig or ipconfig, you should see an IPv6 address there. And notice, it should be starting with FE80. That is your link local address. Now, what is the purpose of a link local address? It is used for, okay, I think I've mentioned a little bit about auto configuration or SLAC, stateless address auto configuration. Okay, for simplicity, just call it auto configuration or autoconf. Now, it is used for that one. So the moment that you enable your IPv6 on your network, you don't need to assign an IPv6 address. You can reach other machines only within your local link using that IPv6 address. Again, reminder, that's only within the local link. It cannot pass through a router, only within the local scope. Okay, so I hope that's clear with everyone. That is your link local address. It's a very important address in IPv6. The next one that we have here is site local address. Now, this one, okay, I'll tell you outright, is already deprecated. We don't use it. The reason I have this here is, of course, for you to understand different types of addresses, and because it is important for the next one. What is a site local address? Sometimes we call it as SLA. The idea here is very good. It should be similar, okay, to RFC 1918. So RFC 1918 is your private addresses, 192.168.1.0, 172.16, and 10/8. Those are private addresses on IPv4, and they are defined in RFC 1918. In IPv6, we want something like that, right? So only available within the local scope. It's not reachable to the rest of the internet. It's not routable to the rest of the internet. So we use FEC0, and it's defined in RFC 3879. Now the problem with this is also kind of like simple. So here we are defining a site, and sites have a fuzzy definition in it. Sometimes a machine can belong to one very small site and also belong to a bigger site. So the problem is, if you belong to those two sites and there's kind of an overlap, what happens to the IP address? If there are two machines in those sites, okay, they can have similar, or sorry, not similar, exactly the same IP address. Therefore, okay, it will have a conflict. As you know, IP addresses in general cannot be the same. They have to be unique on a single machine. So because of that ambiguity in the definition of the site, okay, they decided to deprecate this and replace it with unique local address, or ULA. ULA, the purpose is the same, representation similar to RFC 1918, but here it will be unique. It will be unique anywhere in the world. Okay, you can use some tools, you can use an algorithm to generate this. So no two IPv6 address, unique local address, or ULA, cannot have the same address. Okay, that's just not technically feasible with the algorithm. Now, why do we have this? Again, it's a kind of like a local address. It's FC00/7. So you can assign, say you have a machine. You already have a link local address on that machine. Okay, it's only reachable within the local link. But in your network, you probably have different subnets. Maybe you have one in your finance department, your IT department, your executive committee, maybe. So how can you now reach other machines within your network if cannot pass through a router? So you can use a unique local address in that sense. Think of it as your local private address in IPv4. All right, so that's ULA. The last one here is global unicast address. So obviously this one is your routable IPv6 address. These are the ones you should get from your upstream providers or from APNIC. So the block for global unicast address is 2000/3. I think some of you have seen this earlier. We have subdivided this /3 block into smaller /12 blocks. So you have 512/12s. Now 5 of those /12s have been given to each of the 5 RIRs. In our region, we have 2400/12. So right now, within IANA, they have 506 spare /12s. One of the /12 is used for miscellaneous purposes, for testing, for experiments, for other types of addresses. The other 5 is the ones that have been distributed to the RIRs. So 6 have been in use right now, okay? And then 506 is still within IANA pool. Okay, so if you want to implement IPv6, of course, and if you have machines, routers, servers that should be reachable on the global IPv6 internet, then you should assign a global unicast address to it. Any question? Okay, so those are some examples of unicast addresses. If you still remember, what is a unicast? It's assigned to a single machine. Now this other one is 2002/16. Now this is another network prefix that has a purpose. Its main purpose is for transition. So for a time in the earlier days, transitioning from IPv4 to IPv6 can be a pain, but there are different transition techniques, transition mechanisms. One of those is 6 to 4. If you're going to use this transition mechanism, you already have a block that is assigned specifically for that, 2002/16. Okay, so if you're implementing 6 to 4, then this is the block that will be used. Okay. Other blocks you have here, documentation prefixes, 3FFF/32 and 2001DB8/32. In a lot of my examples here, you see me using 2001DB8. And the purpose is very easy. It's only used for documentation, for examples, for writing journals, for writing documentation for your company, network, and things like that. Okay, you don't want to mess around with live IP addresses, because of course it can have an effect on other networks. So for documentation, just use either of these two. So this is just a summary of all of those IP address blocks that we have discovered and discussed so far. This is the global unicast 200/3, unique local address ULA FC00/7, link local address is FE80. This one, FEC0, used to be site local address, right? SLA, but we're not using this anymore. That's why it's now reserved. FF00 is for multicast. 2002/16 is for 6 to 4 addresses. Okay, so at this stage, if you see a type of address, or if you look at your network interface, if you see an IPv6 address there, you should be able to pinpoint what type of IPv6 address it is. Is it unicast or multicast? And what is the purpose of that? So give that one a try when you have some spare, and test yourselves if you can do it. Any questions so far? Are we still clear? Everyone still following me? If you're having issues, just please let me know. If you have questions and other things, again, just please let me know so I don't have to go. If I'm going too fast, also let me know. All right, so as I've said earlier, the last few slides were about network prefixes. Here, Okay, we talk about the last 64 bits, which is your interface ID. What is the interface ID? It's the lowest 64 bit of your address, and it's assigned in multiple ways. Now, before I look at that, how do you actually assign an IP address on a machine? Think about it. How do you assign an IP address on a machine? If it's IPv4, you use multiple ways. One, you assign it statically. Another one, you use DHCP, right? Those are the two main things. In IPv6, you can still do that. You can assign it statically, all those 128 bits. It can be a bit of a pain if you have to assign, say, 1,000 different machines with IPv6, right? So another way is to use DHCP, okay? And there are a few other ways, okay? You can use eIP602, or you can use auto-generated pseudo-random numbers. Actually, those two are the most common ones. Before we go on to the details, I'll just try to answer Camila's question there. In case of, is it corporate LAN, private IPv6 addresses can be used. Yes, technically you can use a private IPv6 address, okay? But if you already have a global unicast address, I would suggest to use that. One reason is because, let's say for example right now, you have a corporate LAN network, and then you want, say, to send or transmit IPv6 traffic going to your upstream providers. That should still work. Your upstream provider should support IPv6. Okay, they can give you a public global unicast address block, okay, IPv6 block, and then you just use that on your routers. But you can also use that same block for the rest of your network. IPv6 is so big, so that should be easily done. Now later on, if you have another upstream, maybe you decide to do multicast, sorry, not multicast, you decide to have multi-homing. So you have two upstream providers or maybe even more. As your network grows, there might be a need for that. So you can then easily use that network and then ask to announce that IPv6 prefix to your other upstream. That's one possibility. But obviously, ideally, if you just want to run IPv6 locally, yes, you can do that. And if you want, locally you have IPv6, and then going outside to the IPv4, say, network, you'll have something like a translator box, v6 to v4. You can also do that. Okay, so I hope that answers your questions. Obviously, we need to discuss it a bit further. It will depend on your setup too. Okay, let's move on. So I said that for interface ID, normally you use eIP602 or auto-generated pseudo-random number. Let's look at the first one. It's actually called modified eIP602. Now this one is based on your MAC address. So some of you, I think, were looking at your IPv6 address earlier. Okay, your linked local address. You have your FE80, and then the last bits. Notice what type of, what's in there. What is the contents of your interface ID? Two possible things. One is it's eIP602. If it's eIP602, it's based on your MAC address. So check your MAC address, okay? And then what happens is you divide that MAC address into two, insert FFFE there, and then the 7th bit here, you toggle from 0 to 1. So if you notice, say FE80 colon something something, and then you have an FFFE, usually that's your link local address if you're using modified eIP602. You can go have a look. Now the other one, well, it's not actually here, but one of the issues or problem that some security people found with this is its dependency with a physical address. As you know, physical addresses or MAC addresses are unique to a single machine. So wherever you go, you carry that with you. So if I'm connected here at the APNIC office and I'm using our IPv6 network, I might get a network prefix and then use on the interface ID. I will still use my own eIP602, right, to form or to complete the IPv6 address. If I move to another place, maybe I'm traveling to Singapore, then if I connect to an IPv6 network, it's the same. My interface ID will not change because it's based on my own MAC address. So security-wise, some people said that maybe this can be used as a vector for, say, hackers or bad people out there as a form of attack. So aside from eI64, there is now an option to use pseudorandom numbers. So that one's easy. Your machine, your operating system, will generate this automatically for you. If you're using Windows, by default, it uses pseudorandom numbers. You can always change that to eI64, but by default, it will just give you a set of random values for your interface ID. If you're using Mac or Linux, I think the default is eI64, but you can always opt to use pseudorandom numbers. Okay, so those are the two ways to assign values to your interface ID. Okay, next one is zone IDs. Now, someone asked this question earlier. So assume that you have two machines. In this case, host A and host B. What type of IP address are you using? Link local address, right? What type of interface ID? This is using FFFE. You notice there, it's eI64. So within the local link, you should be able to access each other's machines. You should be able to ping from host A to host B. Now you notice that at the end of your IP address, you have something like %4 or EN1, EN2, something like that, depending on your operating system. That is what we call as a zone ID. What is a zone ID? A zone ID is unique to your machine. It's generated by your operating system. It's a unique identification for this address assigned to this interface. Because in one interface, you can have a linked local address. You will always have a linked local address. You can also have a unique local address, a global address. You can have more than one of those. So at the very least, you might have 2 or 3 IP addresses on a single network interface. So this one identifies to where your packets will go out. Okay, how it will send the packets for you, which network is the packet intended for. So let's say I ping from host A to host B. Notice that I ping the address of host B, in this case 3001, right? 3001, but I'm using zone ID %4. Okay, %4, which is my zone ID. Again, that's because the zone ID is only defined locally. It doesn't get out of your machine. It doesn't get out of your system. Okay, you only identify that to which zone this particular traffic is intended for, to which network. Does that make sense? It identifies the interface zone ID on the host, which is connected to that segment. So not the neighbors, but your own zone ID. Now, if you try to do a simple ping, okay, your machine right now should be intelligent enough so you don't really have to use zone IDs. But in some cases, you might need to. So if you think that it's not working by just doing a simple ping without the zone ID, try it with your own zone ID, and it should definitely work. Okay, give that one a try. So any questions so far? I think we've already discussed quite a lot. There's still a few things to discuss. Here is about auto configuration. What is auto configuration? You can have automatic IP address on your machine by auto configuration, right? There are 2 ways that you can assign an IP address to your machine. It's either stateless or stateful. Stateless is when you're not exactly concerned with the IP address of the machine. It's an end user machine. Okay, no one will have to connect to it. You're the one connecting to other machines using that machine. Okay, if you're not concerned with the exact address of that end user machine, then you use stateless mechanisms. If you are concerned with the actual address and you don't want it to be changing every time, then that is what we call a stateful mechanism. So this is usually for servers, for some of your network devices, routers, and things like that. So for that, you might need a DHCP v6 server. For stateless mechanism, no need because your machine will generate automatic IP address for you. Now this is how it actually works, right? At the back end, if you turn on a new machine, it will have a tentative address. Obviously, it's a link local address because it's a mandatory address. So your link local address is based on the prefix F80 plus your interface ID. Now, this one example is using EUI64. This is still a tentative address, meaning it might change. So I have to check whether this is unique in my local network or not. So I will send a check to all of the other machines that are connected to this. This is what we call as duplicate address detection. Okay? In IPv6, if you remember, we don't have broadcasts. We have, we're using multicasts. And within that, we don't have what we call as ARP, Address Resolution Protocol. The equivalent of ARP in IPv6 is what we call as NDP, Neighbor Discovery Protocol. So in NDP, you're sending messages, neighbor solicitation, neighbor advertisement, router solicitation, router advertisement. Now for duplicate address detection, you are sending a neighbor solicitation message. Okay, you send that so you know if someone is listening to that particular multicast address. That multicast address is what we call as solicited node multicast address. So one thing that you should know, once you have an IPv6 address on an interface, it will have a corresponding multicast address. That corresponding multicast address is what we call a solicited node multicast address. So when I send a message to this address, if it's unique, then I should not get a response. Correct? I should not get a response because I'm the only one using that address. But if someone already uses that address, then I will get a reply. You will get what you call as a neighbor advertisement or NA. Now, if you don't receive a neighbor advertisement, you can rest assured that your address is correct, it's unique, so you can now assign that address to your interface. Does that make sense? Okay, the next part is looking for routers. So you want to assign either a unique local address or maybe a global address. Who gives you that? Okay, that prefix is being advertised by your router. So the router will give it to you, but first you have to look for that router. You look for a router to get a router advertisement. So that's what we call as router solicitation. I will send it to the all routers multicast address. Again, this is another multicast address, FF02::2. If there is any router in my network, okay, it should be listening to this multicast address. So I will receive that router solicitation message, and then this router will now send a router advertisement or a router advertisement. Now the router advertisement typically only contains the prefix. So the interface ID will still be up to you. Okay, you will only assign the prefix, which in this case is 2001:1234:1:1. The rest, if you notice from here, okay, is very similar to the interface ID that we have for our link local address. Okay, because that's interface ID, it's generated using EUI64. So that's how you do it. So at the end of it, you can now assign either a ULA or a global unicast address for this same interface. So in this example, we have gone through two steps, neighbor discovery and router discovery. At the end, we have two IP addresses assigned on the same interface, one link local, one global or unique local address. Any questions? All right, I don't see any questions. I hope that it's clear with everyone. Okay, that's kind of like a big concept that you have to kind of digest within you. So I'll leave it at that, but if you have further questions, please feel free to chat. Next one is subnetting. Now you have an IP address already. By default, you will get a /32 IPv6 block from APNIC. If you request, if you are an ISP, okay, if you have an allocation for IPv4 already, then you can be eligible to get a /32 IPv6 address. So in this case, I have 2001 db8/32. So what you want to do after you have your IPv6 block is to distribute that, right? We have customers. Maybe you want to give /48 blocks to each of your customer. So what do you have to do? This is where subnetting would come in. And subnetting in IPv6 is kind of very similar to how you subnet in IPv4. So if you're familiar on how to do subnetting in IPv4, okay, the process is actually very similar. The concept on how you do it is very similar, but the block sizes are obviously bigger. Here you have /32. If you think about it, how big is a /32 IPv6? That's already equivalent to the entire IPv4 address space. So that's big. So here you have a /32 block, and then subdivide that into smaller pieces, /48s for your customers. So in this example, it's asking only for the first 4, okay, so that you can list them down. And this is how I would normally do it. I'll just give you this example, and then you can work your way to some of the exercises that I have after this. So I have this /32. I want to subdivide this into /48. Where is /48? Okay, that's the very first thing that you should know. /32 means 2 fields in IPv6, so 2001 db8. How about /48? That's an additional 16 bits. So that's another field. So notice we have 3 fields for your /48. That's the very first thing. You should be aware that how can you do your subnetting if you cannot do that. Next one, that's your network prefix now. Next one, how many /48 blocks are there in a /32? Okay, that's a simple question, and you answer that using exponentials. /32 over /48 gives you 2 raised to 16. You can actually have 2 raised to 16 /48 blocks in a /32. So let's proceed with the itemizing only the first 4. So just to make it easy, you don't have to list down all 2 raised to 16 values, only the first 4. So how do you do that? You start by manipulating the least significant bits of your network prefix. So our /32 is somewhere here, our /48 is here. So you can manipulate this third field. Okay, so it's simple. The first thing is you can write this down in bits. Okay, this is not properly formatted here, so hopefully you can still understand. But just write down the that last field in bits. So there should be 16 bits, and then you do your increments. So you have there 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, and 0, 0, 1, 1. But remember, here we are discussing about hex. IPv6 should be hex values. And the red values here are in bits, in binary. So you have to change it back to hex. So that's 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 2, and 0, 0, 0, 3. So you look at the last nibble there. That's 0, that's 1, that's 2, and that's 3. If you notice that a simple incrementing if you're working on hex. But if you happen to be working on an odd value, meaning it's not for the entire field, okay, or maybe it's not in the nibble boundary, then it might be harder for you to just work on it just looking at the hex value. So it might be good to do it step by step. First, write them down in bits, do your increments using bits, binary, and then you convert it back into hex digits, such as this example. All right, so this we have an exercise. Okay, I have 3 exercises for you to do. Okay, I'll leave you to do it on your spare time. You can obviously find the answers on some of our uploaded videos. But if you want to verify with me, you can always send me an email. My email address should be in the slide set. So as a challenge for you at the end of this, okay, once we've finished, please try to do these exercises. The first one, identify the first 4 /36 given a /32. Now that one should be easy. It's very similar to the example that we give. The next one is identify the first 4/35 given a /32. Now this one is a little bit more difficult than the first one. Notice we're using /35. It's not in the nibble boundary. And then this last one, oh, actually I only have two. That should be right. I only have two examples for you. So please try this and then give me some feedback if you were able to get it or if you have further questions. All right. So I think we will end there. That's the end of this presentation. We have some materials on the APNIC website if you want to learn more or find some case studies that you can possibly follow with your IPv6 transition. If you have further questions, send them to training@apnic.net. Now, just to wrap things up, the feedback form is on this link, so please click on this link, just a couple of minutes, and then you should be able to get a copy of the slide handouts once you're done. I'm also going to write down the link to these slides. If you don't have it yet, this is where you can download the handouts for today's sessions. Okay, the recorded videos, this one I'm not sure when I'm going to upload this, but if you go to youtube.com/apnic training, we have previous recordings of this same session. Okay, but for this one, I can't really assure you when we're going to upload it. Sorry about that. But yeah, you can go have a look at our other recorded videos there. Any other questions, guys? If none, I think we should end there. Thank you very much for your time and your attention. We will have another session later on, so please stay tuned. And that's in about an hour, 3 o'clock, 1 hour from now. You can also join that. Thank you very much again, and I'll see you in another e-learning session. Bye-bye.